everybody. It's now time to discuss the questions on probability. Let's begin with the first question. It says that in a cricket match, a batswoman hits a boundary 6 times out of 30 times she plays. Find the probability that she does not hit the boundary. Now, please try to understand this in the very terms of probability. We know that if an experiment is performed n times, that means n trials of that random experiment are performed, out of those n trials an event A is occurring in some m trials, then the probability of occurrence of event A is m upon n. Now you can over here consider the number of balls that she plays as the number of trials, right? So over here the experiment is that she is playing and hitting the ball, clear? And the balls are actually coming 30 times, okay? So total number of trials of this experiment is 30. So total number of trials is 30, okay? If I say event A is hitting of boundary, event A is hitting of boundary, then she is able to hit the boundary in 6 balls out of 30 balls. So, number of trials in which event A is occurring are 6. In 6 hits or in 6 plays, she is hitting the boundary. So, number of trials in which A occurs is 6. Number of trials in which A occurs is 6. Out of 30 trials, in 6 trials event A is occurring. What do you think will be the number of trials in which she will not be able to hit the boundary? So, number of trials in which she does not hit the boundary. Hit the boundary. Out of 30 in 6 trials, she is hitting the boundary. So, 30 minus 6, that is 24 trials are there, 24 balls are there which she is playing, but she is not able to hit the boundary. If I declare not hitting the boundary, not hitting the boundary as event B, then number of trials out of 30 trials, out of 30 plays of hitting the ball, number of plays in which B occurs, that means in which she is not able to hit the boundary, a 24. In 6 balls she is able to hit the boundary, in 24 she is not able to hit the boundary. So, total number of trials are 30. Out of these 30, number of trials in which B occurs is 24. So, probability of event B, which is probability that she is not able to hit the boundary, is what is probability of B? It will be 24 upon 30. Clear? Let's look at the next question. In a particular section of class 9th, 40 students were asked about the months of their birth. So, there are 40 students in the class. Each student is being asked about the month in which he or she was born. And the graph is prepared for the data so obtained. In January, 3 students are born. In February, 4 students. In March, 2 students. In April, also 2 students. In May, 5 students. In June, 1 student. In July, 2 students are born. In August, 6 students are born. In September, 3 students. In October, 4 students. In November, also 4. And in December, also 4 students. That's how the data was collected about the months in which these 40 students individually were born. The question is, find the probability that a student of the class was born in August. Clear? Now, there are 40 students, so total number of trials with me are 40, right? Total number of trials with me are 40. That means the total number of students that I have about which I am collecting information about the months in which they were born are 40. Out of those trials, how many trials are in favor of this particular event of being born in August? How many are in favor of this particular event of being born in August? In August, 6 students are being born. So, out of 40 trials, 6 trials are in favor of this event. So, 6 upon 40 will be the probability of this question. So, what you have, total number of trials is right now 40, right? A is the event of being born in August. out of 40 students, how many students are born in August? That means out of 40 trials, how many trials are in favor of A? How many trials are in favor of A? That means in how many trials event A is occurring? Out of these 40, only 6 are born in August. So number of trials in which A occurs is 6, and therefore probability of occurrence of event A, that means probability of student being born in August, is 6 upon 40. Is it clear? Let's look at the next question. A die is thrown 1000 times with the frequencies for the outcomes 1, 2, 3, 4, 5 and 6. Now you know that when you throw a die, there are 6 possible outcomes, 6 elementary events associated to it, right? So 6 possible outcomes, and 1000 trials of this throwing a die have been performed. So total number of trials in this question is given to be as 1000 trials are performed. In each trial you get an outcome from 1 to 6. Okay, 1000 trials have been performed. It is saying in those 1000 trials, 1 is coming as an outcome in 179 trials, 2 is coming as an outcome in 150 trials, 3 is coming as an outcome in 157 trials, 4 is coming as an outcome in 149 trials, 5 is coming as an outcome in 175 trials out of 1000 trials, and 6 is coming as an outcome in 190 trials. When you add 179 plus 150 plus 157 plus 149 plus 175 plus 190, you get 1000. So that's how you are getting outcomes in 1000 trials. Outcomes can be ranging from 1 to 6 only. That is what the outcomes you get when you throw a die. So each outcome is coming how many times is being written over here because the die is being thrown 1000 times. What is the probability of getting each outcome? So say total number of trials is 1000. I will be defining different events. So first is event A, which is getting 1 as the outcome. Getting 1 as the outcome. Now 1000 trials are being performed. In how many trials you are getting 1 as the outcome? You are getting 1 as the outcome in 179 trials. So A is getting 1 as the outcome. Number of trials in which A occurs is 179, and therefore probability of occurrence of A is 179 by 1000. So probability of occurrence of 1 as the outcome is this. If I define B as getting 2 as the outcome, the number of trials in which event B occurs, number of trials in which you are getting 2 as the outcome is 150. So you are going to write 150 here, and therefore probability of event B will be equal to nothing but 150 upon 1000. Next is 3. So if I define my event C as getting 3 as the outcome, the number of trials in which event C occurs is 157, and therefore probability of occurrence of event C is 157 upon 1000. Exactly in a similar fashion, if I say D is getting 4 as the outcome, the number of trials in which event D occurs is 149, and therefore probability of occurrence of event D is 149 upon 1000. It is 149 upon 1000. Similarly, if I say event E, if I talk about event E, then event E is getting 5 as the outcome, and out of 1000 trials, 5 is coming as an outcome in 179 trials. So event E is occurring in 179 trials. So probability of occurrence of event E is 179 upon 1000, 175, not 179, 175. And last, you define event F of getting 6 as the outcome. Number of trials in which event F occurs is 190. So probability of occurrence of event F is 190 upon 1000. Is it clear? These are your respective probabilities. Let's look at the next question. It says that on one page of a telephone directory, please try to read the question nicely. On one page of a telephone directory, there were 200 telephone numbers written. The frequency distribution of their unit place digit. That means, now see, when you have a phone number, suppose this is a phone number, it has a units place, right? The unit place digits were collected. Now, in the unit place, you can have either 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. The moment it becomes 10, it becomes a 2-digit number. So, in the units place, you can have a single digit number ranging from 0 to 9. In those 200 telephone numbers, 0 was sitting as a unit digit in 22 phone numbers. 1 was sitting as the unit digit in 26 numbers. 2 was sitting as the unit digit in 22 phone numbers, 3 was sitting as the unit digit in 22 phone numbers, 4 was sitting as the unit digit in 20 phone numbers, 5 was sitting as unit digit in 10 phone numbers, 6 was sitting as unit digit in 14 phone numbers, 7 sat as unit digit in 28 phone numbers, 8 sat as unit digit in 16 phone numbers, and 9 as unit digit in 20 phone numbers. When you add 22 plus 26 plus 22 plus 22 plus 20 plus 10 plus 14 plus 28 plus 16 plus 20, you get 200. Question is, without looking at the page, the pencil is placed on one of these phone numbers. That is, the number is chosen at random. The phone number is chosen at random. So, choosing a phone number out of these 200 phone numbers is my experiment. Fine. Out of these 200 phone numbers, if I am choosing a phone number at random, which phone numbers can come up as possible outcomes, as possible selections? Any of the 200 can come. So, how many possible outcomes I have? How many possible outcomes I have when I am picking up one phone number out of these 200? 200 possible outcomes I have, right? Over here, I will say total number of outcomes that I have is 200, and I have to find the probability that the digit in the unit place is 6. I have to find out the probability that the very phone number that is being selected has unit digit as 6. So, if total number of outcomes are 200, okay, 200 phone numbers are there, any one can be selected, so 200 possible outcomes are there. Total number of possible outcomes are 200, and number of outcomes which are favoring this event of getting a phone number in which unit place is 6. So, let me say A is getting 6 in units place. That means the phone number that once got selected when you are performing this experiment of selecting a phone number from 200 phone numbers, the phone number which is getting selected is having 6 in the unit place is what is event A. How many outcomes are actually favoring event A? Out of the 200 phone numbers, there are 14 phone numbers which have 6 as the unit place. When out of these 6, any one phone number will be selected, then I will say event A has occurred, right? Out of these 14 phone numbers, when any one phone number will be selected, I will say in all those 14 situations, event A is occurring. So, out of the 200 possible outcomes, how many possible outcomes are there which are favoring my event A? These 14 outcomes. When as an outcome I will get any one of these 14 phone numbers, then I will have event A occurring. So, I will have number of outcomes or phone numbers. Number of phone numbers are my outcomes. Number of outcomes in which A occurs is 14. So, probability of A is number of outcomes in which A occurs upon total number of outcomes. Is it clear? Let us look at the next question. The record of a weather station. The record of a weather station shows that out of the past 250 consecutive days, its weather forecasts were correct 170 times. So, 250 consecutive days the forecast was checked and it was correct 175 times. What is the probability that on a given day it is correct and on a given day it is not correct? So, total number of days on which I have checked the weather forecast is 250. Right? So, from each day I have a report. So, total number of outcomes that I have is 250. The outcome is nothing but the report of that particular weather forecast. So, total number of possible outcomes is 250. Out of 250 possible outcomes, on 175 days it was correct. That means 175 reports about weather forecasts got to be correct. So A is that report is correct. So out of 250 reports, or the results of 250 reports, 175 results are favoring A. So number of outcomes in favor of A is 175, and therefore probability of A is 175 by 250. A is what? Report is correct. That means A is that on a given date is correct. So we have found out the probability of the first case. What is the probability that it was not correct? So out of 250, 175 is correct. So if I say event B is report is incorrect, then number of trials or number of outcomes in favor of B, it is 250 minus 175, which is 75. Right? Out of 250 reports, 175 reports said that it is correct, and 75, rest of the 75, it was incorrect. So probability of event B will be 75 upon total number of outcomes, which is 250. Is it clear? Let's look at the next question. The distance of 40 engineers from their residence to their place of work. The distance of 40 engineers from the residence to the place of work is found to be this. So these are 40 numbers written over here, each representing distance in kilometers from the residence to the workplace of these 40 engineers. So this is the data of 40 engineers. What is the empirical probability that an engineer lives less than 7 kilometers from her place of work, right? So here the data is being collected of 40 engineers. How many values out of these 40 values are favoring this first event, favoring this second event, favoring this third event? So if I say A is less than 7 kilometers from the place of work, what is the probability that an engineer lives less than 7 kilometers from her place of work? So living less than 7 kilometers. Let's see. Out of 40 engineers, how many engineers live less than 7 kilometers away from their place of work? Less than 7. 5 is less than 7, 3 is less than 7, then you have 2 is less than 7, then you have 3 is less than 7, 5 is less than 7, this is less than 7, this is less than 7, then you have this is less than 7, this is less than 7. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 40 engineers, 9 engineers live less than 7 kilometers. So 9 outcomes are actually in favor of event A. So probability of A would be 9 by 40. If I say B is more than or equal to 7 kilometers, living more than or equal to 7 kilometers, more than or equal to 7 kilometers. If out of 49 are living less than 7 kilometers away, rest of them are living greater than or equal to 7 kilometers away, obviously. So how many are in favor of B? How many engineers are living greater than or equal to 7 kilometers? 40 minus 9, that is 31 engineers are living either 7 kilometers away or greater than 7 kilometers away, because only 9 are living less than 7 kilometers away. So out of 49 are living strictly less than 7 kilometers away, rest all are living greater than or equal to 7 kilometers away, right? And therefore probability of B is 31 upon 40. Similarly, I have event C, which is within half kilometer. So living within half kilometer, less than half kilometer, that is 0.5. Is there any engineer who is having its distance from residence to workplace as less than 0.5 or even 0.5? No. There is no engineer whose distance from their workplace to their residence place is less than half. minimum 2 kilometers is the distance, and therefore there is no engineer which is living less than half kilometers away, and therefore probability of C is 0 upon 40, because there is no engineer which is living half kilometers away. So out of 40, no engineer is living less than half kilometers away. So 0 upon 40 is the probability of C. C is an impossible event. This can never ever occur. Clear? Because no engineer out of these 40 engineers is satisfying this condition. Next, 50 seeds were selected at random from each of the 5 bags of seeds. So there are 5 bags of seeds and I am selecting 50 seeds from each bag, and for 20 days I am keeping it under standardized conditions to germinate. After 20 days I am seeing that from the first bag only 40 seeds have germinated, from the second bag 48 have germinated, in the third bag out of 50 42 have germinated, in the fourth bag 39 have germinated, and in the fifth bag 41 have germinated. In total I have 5 bags, and this is the data corresponding to the number of seeds out of 50 seeds which have germinated in each bag. I have to find the probability of germination of more than 40 seeds in a bag. So if event A is that more than 40 seeds have germinated, well, in total I have 5 bags. If I talk about the number of bags in which more than 40 seeds have germinated, more than 40 has been germinated in the second bag, in the third bag, in the fifth bag. So more than 40 seeds have been germinated in 3 bags out of 5 bags. So 3 by 5 is probability of A. Event B is 49 seeds in a bag. 49 seeds have germinated. So out of 5 bags, in how many bags 49 seeds have been germinated? 49 seeds exactly have been germinated in no bag. So 0 upon 5 is the probability of event B, that is nothing but 0. Next is more than 35 seeds. Greater than 35 seeds have germinated. Greater than 35, this is greater than 35, greater than 35, greater than 35, greater than 35, greater than 35. So in all the 5 bags, out of the 5 bags in each bag, more than 35 seeds have germinated. So out of 5 bags, in all 5 bags this condition has been satisfied. So probability of C is 5 by 5, which is 1. So C is a sure event or a certain event because its probability is 1. Next question says, a tire manufacturing company kept a record of distance covered before a tire needed to be replaced, and this table is showing 1000 such cases. That means there were 20 vehicles or there were 20 tires which got changed after covering less than 4000 kilometers. 210 tires got changed when they had covered distance between 4000 to 9000. 325 tires got changed when they had covered distance from 9001 to 14,000 range, and 445 tires had to get changed when they had covered more than 14,000 kilometers distance. If you buy a tire of this company, what is the probability that it will need to be replaced before it has covered 4000 kilometers? Right? Here the data is being collected of 1000 tires. Okay? Total 1000 tires are there. What is the probability that the tire will have to be replaced before it has covered 4000 kilometers? So if it has covered less than 4000 kilometers, then the data is 20. 20 tires had to be replaced when they had covered distance less than 4000. So out of 1000 tires, 20 tires had to be replaced before they had covered a distance of 4000. So what would be the probability then? So if I say is tire getting replaced, before covering 4000 kilometers, So out of 1000 tires, 20 tires are favoring this event because they are getting replaced in less than 4000 kilometer distance. So probability of A will be 20 upon 1000. Similarly, if I define B as it will last more than 9000 kilometers, that means more than 9000 it will last. What is the probability that the tire is going to last more than 9000 kilometers? That means it will have to be changed after it has covered 9000 kilometers, or it will last more than 9000 means what? Here the tire is supposed to be changed when it has covered distance between 9000 and 1 to 14,000. Here the tire is getting changed when it has covered more than 14,000 distance. What is the probability that you will need to change the tire once it has covered more than 9000 distance? More than 9000 is these two cases. In this case 325 tires need to be changed, in this case 445 tires need to be changed. So if I talk about event B, that tire is getting replaced after covering 9000 kilometers, that means it can lie in this range and it can lie in this range. 325 tires are favoring this event because they are getting replaced when they have covered this much distance, that means distances beyond 9000. 445 tires, even these 445 cases are also favoring event B because they are signifying that the tires are getting replaced when they have covered more than 14,000 kilometers distance, when 14,000 is obviously greater than 9,000. So 325 plus 445 is the number of tires which are getting replaced after covering 9000 kilometer distance. So out of 1000 tires, 325 plus 445 tires favor my event B. So probability of event B is 325 plus 445 upon 1000, which is 700 upon 1000. Clear? Then if I define event C as it will need to be replaced after it has covered somewhere between 4000 to 14,000. Somewhere between 4000 to 14,000. Okay? Out of 1000 tires, 210 tires are replaced when they have covered distance in this range, which is after covering 4000, and 325 tires need to be replaced after covering distance in this range, which is between 9000 and 1 to 14,000, that means less than 14,000. These are which are getting replaced after covering 14,000 kilometers. So in the range of 4,000 to 14,000, I have these two numbers. So out of 1000 tires, 210 plus 325 tires are actually favoring my event C, which is getting replaced after covering distance in the range of 4,000 to 14,000 kilometers. How many are favoring event C? 210 plus 325 tires. So you have 210 plus 325 is 535. So you have probability of C is 535 upon 1000. Is it clear? Let's move to the next question. An insurance company selected 2000 drivers at random. Okay, so at random 2000 drivers have been selected in a particular city to find a relationship between age and accidents. The data obtained is here. Drivers whose age was ranging from 18 to 29, for them the data is that no accident is happening with 440 drivers. 160 drivers are getting exposed to one accident, 110 drivers are getting exposed to 2 accidents, 61 are getting exposed to 3, and 35 drivers are there who have already witnessed 3 accidents, over 3 accidents. In the age group of 30 to 50, 505 drivers have witnessed no accident, 125 drivers have witnessed 1 accident, 60 drivers have witnessed 2 accidents, 22 drivers have witnessed 3 accidents, and 18 drivers are there in this age group of 30 to 50 who have witnessed over 3 accidents. Above 50 are 360 drivers who have witnessed no accidents, 45 drivers have witnessed 1 accident, 35 have witnessed 2, 15 have witnessed 3, and 9 have witnessed over 3. Out of 2000 total number of drivers, what is the probability that being in the age group of 18 to 29 years and having exactly 3 accidents in 1 year? So, if event A is having exactly 3 accidents in a year, being in the age group of 18 to 29, having exactly 3 accidents in a year, there are 61 drivers out of these 2000 drivers which are favoring the condition of this event. There are 61 drivers who are being exposed to 3 accidents in a year falling in the age group of 18 to 29. So, probability of event A will be 61 upon 2000. Similarly, event B would be being in the age group of 30 to 50 and having 1 or more than 1 accidents in a year. So, having 1 or more than 1 accident. And obviously, this is regarding 18 to 29 age group and this is regarding 30 to 50 age group. Clear? Having 1 or more than 1 accident. If you are in the age group 30 to 50, 125 are being exposed to 1 accident, 60 are being exposed to 2, 22 to 3 and 18 are above 3. So, at least 1 accident in this age group of 30 to 50 is happening with how many drivers? 125 plus 60 plus 22 plus 18. It is these many drivers 125 plus 60 plus 22 plus 18 which are in the age group of 30 to 50 and they have at least 1 accident in a year. 125 have exactly 1 accident and 60 plus 22 plus 18 have at least 1 accident because 60 have 2 accidents, 22 have 3 and 18 have over 3. So, how many drivers are there which are favoring this event of having 1 or more than 1 accident falling in the age group of 30 to 50? I have 125 plus 60 plus 22 plus 18. These are the number of drivers which are actually having 1 or more than 1 accidents in a year falling in the age group of 30 to 50 out of the total of 2000 drivers. So, probability of B is this number, you can very easily evaluate. Then you have having no accident in 1 year. Having no accident in 1 year, there is no age group specified. Having no accident. So, out of 2000 drivers, how many drivers are there which are having no accident in a year? 440 drivers in the age group of 18 to 29 are having no accident in a year. 505 in the age group of 30 to 50 are having no accident in a year and 360 in the age group of above 50 are having no accident in a year. So, 440 plus 505 plus 360 is the total number of drivers which are having no accident in a year out of 2000. So, probability of event C would be 440 plus 505 plus 360 upon 2000. Is it clear? Let us look at the next question. An organization selected 2,400 families at random and surveyed them to determine a relationship between income level and the number of vehicles which they have. The information is this, that 10 families are, or I should say 10 are the number of vehicles in one family if they have, or I should say 0 number of vehicles are there in 10. What should I say? 0 number of vehicles are there in 10 families who have income less than 7,000. Okay? Vehicles per family, either 0 vehicles are there, 1 vehicle or 2 vehicle or above 2. Income is this, either the income is less than 7,000 or in this range or in this range or in this range or 16,000 or more. 10 families have 0 number of vehicles having income less than 7,000. Having income less than 7,000, 160 families are there which have 1 vehicle. 25 are there which have 2 vehicles, and there are no families having their income less than 7,000 and having above 2 number of vehicles. If the income is lying in this range from 7,000 to 10,000, then there are 0 number of families who have 0 vehicles. That means at least 1 vehicle every family has if its income is falling in this range between 7 to 10,000. 305 families have 1 vehicle, exactly 1. 27 have 2 vehicles, and there are only 2 families which have above 2 vehicles. The income falling in this range, there is only 1 family which has 0 number of vehicles. 535 families have 1 vehicle, 29 have 2 vehicles, and 1 has above 2 number of vehicles. Falling in this range, if it is the income of any family, then 2 families are there which have 0 vehicles. 469 have exactly 1 vehicle, 59 families have 2 vehicles, 25 families have 0 vehicles. And if families have income more than 16,000, then there is only 1 family such which has 0 vehicle, no vehicle. 579 such families have 1 vehicle, 82 have 2, and 88 have above 2. When you add 10 plus 160 plus 25 plus 0 plus 2 plus 27 plus 305 plus 0 plus 1 plus 535 plus 29 plus 1 plus 25 plus 59 plus 469 plus 2 plus 1 plus 579 plus 82 plus 88, you will be getting 2400, which is the total number of families in which this data was collected. Fine. So, total number of families is 2400. What basically do I need to do is, suppose a family is chosen, find the probability that the family chosen is earning income in this range and owning exactly 2 vehicles. Okay? So, event A, I am saying the family chosen is owning exactly 2 vehicles. Okay, and the income is falling in the range of 10,000 to 13,000. Let's see, out of 2400 families, how many families are satisfying this condition. So, out of 2400 families, falling in this range is 1 family, 535 plus 1 plus 29 plus 1, these many families. Out of these many families, how many families are owning exactly 2 vehicles falling in this range? Exactly 2 vehicles are being owned by 29 families. So, out of 2400 families, there are 29 families which are earning income in this range and owning exactly 2 vehicles. So, probability of event A would be 29 upon 2400. Let's see what is the next question. If a family is chosen, what is the probability that that family is earning 16,000 or more per month and owning exactly 1 vehicle? So, 16,000 or more, that is the range of the income, and owning exactly 1 vehicle. Exactly 1 vehicle. Let's see, out of 2400 families, owning 16,000 or more is this range. Exactly 1 vehicle is being owned by 579 families. So, out of 2400 families, 579 families are earning income 16,000 or more and they have exactly 1 vehicle. So, probability of event B is 579 by 2400. Is it clear? Let's look at the next situation. Earning less than 7,000 and don't own any vehicle. So, less than 7,000 and do not own any vehicle. Okay, earning less than 7,000. So, earning less than 7,000, not owning any vehicle, 10 such families. Out of 2400 families, 10 families are there which are earning less than 7,000 and not owning any vehicle. So, here the probability would be 10 by 2400. Next we have earning in this range of 13,000 to 16,000 and owning more than 2 vehicles. So, you have this event D which is saying that earning is lying in which range? 13,000 to 16,000. To 16,000, owning more than 2 vehicles. Okay, owning more than 2 vehicles. Let's look at the situation in the data. earning is between 13,000 to 16,000. Owning more than 2 vehicles are 25 families. 25 families are there out of 2,400 families whose earning is between 13,000 to 16,000 per month and they are owning above 2 vehicles. So, 25 upon 2,400 is the required probability. I have one more event, owning not more than 1 vehicle. No range of income is given, it is just given owning not more than 1, not more than 1 vehicle. That means I can equivalently write this as owning 0 or 1 vehicle, but not owning 2 or more than 2. Either the families should have no vehicle or at the max they should have 1, but they should not have more than 1. So, if I go back to the data, 10 plus 0 plus 1 plus 2 plus 1, this is the number of families having no vehicle. I am not interested in the income range. The event is how many families are having either 0 vehicle or exactly 1 vehicle. So, 10 plus 0 plus 1 plus 2 plus 1, these are the number of families having no vehicle, and 1 plus 160 plus 305 plus 535 plus 469 plus 579, these are the number of families having 1 vehicle. So, number of families having either 0 vehicle or 1 vehicle, I will be adding these 2 columns completely. So, number of families which own either 0 vehicle or 1 vehicle, it is 10 plus 0 plus 1 plus 2 plus 1. This is the number of families having 0 vehicles, and 160 plus 305 plus 535 plus 469 plus 579. This is the number of families having exactly 1 vehicle. So, this plus this is the number of, this total is the number of families having either 0 vehicle or 1 vehicle. Out of 2,400, this that I have written, this number you can evaluate very easily. These are the total number of families having not more than 1 vehicle out of 2,400. And so, this happens to be the probability of A. Of course, you can add this number divided by 2,400 and you get the probability. Is it clear? That is how you tackle questions on probability. That is it from my side. Thank you.